Hello everyone, I'm Javier Cifuentes-Faura from the University of Murcia in Spain. It is an honor to participate in this conference as a keynote speaker. Thank you very much to the organization for inviting me. Today we will talk about energy technologies with a lecture entitled Sustainability and Energy Technologies Funded R&D on Environmental Quality. This work has been co-authored with Emmanuel Uche and Nicolas Enjeva. Issues pertaining to global warming and its mitigative measures have dominated global discourse in recent years. Environmental experts have stressed that surface temperature change is a formidable threat to human existence. World leaders are constantly pushing for policies to make the planet more conducive and livable for all citizens. The adoption of the 2030 Agenda seeks to put an end to problems such as climate change and environmental degradation, reducing pollution and improving the planet and the lives of citizens. The Sustainable Development Goals, decreed by the United Nations as part of the 2030 Agenda, are necessary to, among other things, contribute to economic growth, put an end to inequalities, create sustainable communities, clean energy sources, and fight against climate change. Besides China, the group of 10 G10 countries are currently leading other countries in publicly funded climate change adaptation and resilience projects. They have demonstrated this commitment through publicly funded research and development projects on various energy technologies. These energy technologies include, among others, energy efficiency, renewable energy, nuclear energy, hydrogen and fuel cells, fossil fuels, energy storage technologies, as well as other cutting-edge energy technologies. Accordingly, from 2015 till date, these countries have doubled their investments in energy technologies through policy-funded R&D. This figure illustrates the total publicly funded R&D in all forms of energy technologies in each country. This figure showcases the publicly funded R&D in different categories of energy technologies. An insight from this figure indicates that the United States is leading the rest in publicly funded R&D on energy technologies, followed by Japan, Germany, Sweden, the UK, Italy, France, and Canada, whereas Netherlands and Switzerland are some distances behind. This figure revealed that most of the countries invested more in energy efficiencies, renewables, and nuclear. The figure portrays that power storage technology is receiving the less of the publicly funded R&D budget, particularly in the Netherlands and Switzerland. In countries like Japan, Italy, and Switzerland, energy efficiency technology received less funding than power storage technology. Meanwhile, power storage technology has not received a fair share from the publicly funded R&D in the case of France. In summary, the public allocation to R&D pertaining to these technologies varied substantially both between and within the countries. There is no gainsaying the fact that the empirical literature space is inundated with submissions pertaining to energy technology R&D, carbon emission mitigation nexus. However, what is conspicuously missing is an updated evaluation of the contribution of specific energy technological innovation on environmental quality, particularly after the recovery from the COVID-19 global pandemic. According to some investigations, technological innovation helps to develop appropriate strategies to solve environmental problems and helps to protect and improve the environment. There is a strong argument in favor of the pollution minifying effects of clean energy utilization. Energy technology innovations are expected to drive the ecological transition and, by extension, environmental sustainability. Nonetheless, some discordant views suggested that clean energy and energy technologies R&D finances are ineffective in driving environmental sustainability. Therefore, it is only logical to harmonize this puzzle by extending the empirical evaluation to the contributions of publicly funded R&D on differentiated energy technologies to environmental performance. Such information will enable the adjustments of existing policies and enhance the understanding of the peculiarities of each energy technology. To this end, the study seeks to provide answers to the following critical question. How does aggregate publicly financed R&D on energy technologies influence environmental quality? How does public expenditure R&D on each energy technology, energy efficiencies, renewables, nuclear, power storage, and fossil fuels influence environmental performance? It is expected that the streamlined empirical answer to the above question will have profound effects on policies pertaining to the funding of R&D on energy technologies. The option to either increase or reduce budgetary allocations to such innovation would be clearer. It will also give more impetus to the drive towards pollution-free environmental ecosystems. In this case, policymakers would have a precise understanding of how close they are to achieving SDGs number 7 and 13. Overall, the current study makes some significant contributions to energy technologies and environmental performance theorizations. Firstly, unlike others, this study explored the effects of both aggregate and disaggregate energy technologies publicly funded R&D on environmental quality. Besides, for effective policy moderation, the current study, unlike others, adopted two notable climate change indicators: energy greenhouse gas emissions and surface temperature change for its estimations. The adoption of these two important metrics gave credence to the comparative assessment of the influence of differentiated technological innovation on energy-related emissions, as well as on overall surface temperature change. Furthermore, the study relied on the most updated dataset covering both and pre, during and post-COVID-19 era. The current study provides updated empirical explanation on how publicly funded R&D of energy technologies influence environmental quality in the G10 countries. For this purpose, the annual dataset for the 1985 to 2021 periods was galvanized from reputable data repositories. The data range is essentially defined by data availability. Meanwhile, we transfer the datasets into log values except for the ones on percentage. A more detailed narrative pertaining to the definitions, measurements, and sources of the series is provided in this table. To uncover the underlying relationship between EQ and the least explanatory variables, the study adopted the modified stochastic impacts by relation on population, affluence, and technology STIRPAT framework. In this case, resource rent augments for the population considering the influence of population on resource utilization. The STIRPAT scheme is a modified version of the impact by population, affluence, and technology IPAT scheme credited. The STIRPAT scheme became more prominent since it considers the non-proportional influence of the least variable on the explained variable. Furthermore, in this equation, as you can see in the screen, denote the coefficient of policy-funded R&D on energy efficiencies, renewable, nuclear energy, power storage, and fossil fuels, respectively. Following the above scheme, the total public budget on energy, R&D, as well as its decomposition are expected to promote environmental quality by reducing carbon emissions. On the other hand, public budgetary expenditure on fossil fuels, R&D, will dampen environmental quality by promoting carbon emissions. The underlying elasticities are captured below. Among the control variables of this study, energy tax is expected to enhance environmental performance by reducing carbon emissions, and a negative and positive relationship is expected between GDP and GDP squared and environmental quality following the EKC hypothesis. Likewise, based on the resource cost theory, a negative relationship is expected between resource rents and environmental quality. Hence, the accompanying elasticities are provided accordingly. For the purpose of determining the eventual transnational residual dependence and heterogeneous slope, the study adopted both the Pesaran average correlation coefficient (CD test) technique and a battery of recently proposed weak CD toolkits. In conformity with long-panel data structure, both linear and various newly introducing nonlinear second-generation panel unit root procedures were adopted. In this case, both the linear cross-section Pesaran-Shin and the Pesaran cross-section augmented Dickey-Fuller were selected. This study also evaluated the potential long-term coevolution of the panel variables. The summary statistics revealed that most of the panel variables are divergent in nature. This is demonstrated by the gaps between their maxima and minimum values. Most of the variables have negative tails except E, CO2, NR, and GDP, which have positive tails. By implication, there is potential effects of nonlinearity and asymmetries on the variables. Hence, the study, in addition to conventional panel unit root techniques, employed third-generation panel unit root procedures that account for possible single and multiple structural breaks. Likewise, both the baseline and robustness check models were carefully selected to deal with such issues. The outcome of the correlation matrix portrays that all the enlisted panel variables, except natural resources, power storage, renewables, and energy efficiencies, are positive and strong predictors of environmental quality. Notably, the highest correlation coefficient is recorded between fossil fuels technology budgets and environmental quality, followed by nuclear energy and aggregated energy technology R&D budgets. Furthermore, there is no challenge of multicollinearity among the explanatory variables since none produced a value above the permissible threshold. The outcomes of the cross-section dependency and slope heterogeneity tests are summarized in this table. The sense of cross-section dependency and slope heterogeneity test is to determine the appropriate generation of panel unit root techniques to deploy. Hence, the study employed sets of CD test techniques for comprehensive evaluation since the traditional CD technique may tend to be misleading. Interestingly, both the traditional as well as the newly proposed CD test techniques provided overwhelming evidence not to accept the null hypothesis of cross-sectional independence or weak cross-sectional dependence. This implies that all the panel series are strongly cross-sectional dependent. Hence, the null hypotheses were rejected, and the study adopted sets of second and third generation panel unit root techniques to determine the order of integration of the panel variables. The outcomes of these tests are summarized in this table. Evidence emanating from the second generation panel unit root procedures inform that the relevant variables are mixed integrated. That is, whereas some variables are naturally stationary, others became stationary after differentiating ones. This outcome is consistent in the two procedures adopted. The outcomes of the panel cointegration test that follows the dynamic common correlated effects process unveil long-run coevolution among variables in all the models. On this evidence, the null hypothesis of the ascent on long-run integration is rejected for all the models. Based on this convincing evidence and other identified attributes of the panel variables, the study selected 4 enhanced panel estimators that produce robust outcomes for the ultimate empirical inference. The results of these panel estimators are summarized in the table on the screen. Following the evidence emanating from this table, both the baseline and robustness check models inform that public expenditure on energy technology R&D prove more effective in minimizing energy-induced emissions than climate surface temperature. And now we go with the main conclusions of this study. This study was motivated by the lack of current empirical narratives on how public R&D expenditure on specific energy technologies affected environmental quality. Notably, previous studies succeed in providing narrow accounts of how these factors interacted with environmental quality by considering mostly the total expenditure. Few disaggregated analogies fail to consider several other energy technological innovation R&D funding. Meanwhile, the conclusion of this study remained divergent and ambiguous. It was also noted that the earlier studies were based on datasets that do not reflect current realities. In particular, public investments in energy technology R&D post-COVID-19 increased significantly in most countries. Ignoring this reality undermines the veracity of existing study presentation. To provide streamlined empirical inference, this study concentrated on G10 countries since they are leading in publicly funded energy technology R&D. For precise and updated policy guidelines on how these funds promoted environmental quality, the following steps were articulated. The study galvanized updated annual data for 1985 to 2021 periods from notable data repositories for empirical assessments. To allow for a comparative evaluation to important environmental performance metrics, energy included CO2 and atmospheric temperature pressure were selected. Besides, the study deployed very recent panel estimators that provide robust results irrespective of cross-sectional exigencies and economic shocks. The empirical results reveal that overall R&D expenditure on energy technologies prove more effective in suppressing energy-related carbon emissions than overall climate change. Furthermore, the estimates underscore that among the identified energy technologies, R&D expenditure on renewables, nuclear energy, and power storage curbed both energy-induced CO2 and overall climate change significantly. On the other hand, R&D expenditure on energy efficiencies mitigated only energy-related CO2. Publicly funded R&D on fossil fuel technologies exacerbated both metrics of environmental performance. Among the control variables, it was discovered that energy tax is a significant negative predictor of both pollution metrics. On the other hand, resort rents and GDP remain insensitive to environmental health, hence they promoted pollution significantly. And now we go with some practical implications and policy suggestions. Taking into account the results obtained, the following policy options are essential to sustain the COP27 Green Agenda through publicly funded R&D in energy technologies. Realizing that these funds are capable of promoting clean environments, it is rational to increase this public budget in the future. In particular, more funds need to be allocated to energy efficiency, renewable energy, and energy storage technologies. When this is done, their contributions to the energy transition will also improve. While more funds are allocated to energy technologies, others like nuclear energy should also receive more funding since it is a positive predictor of green economy. Nonetheless, it is essential to redirect attention from fossil fuel technologies since they remain inimical to the net zero emission targets. The focus on electric powered vehicles is well conceived since it has the potential to drastically reduce reliance on fossil fuel powered vehicles. Energy tax must be promoted and supported by all parties since it is a formidable channel to mitigate both energy-induced emissions and overall climate change. It could be more beneficial if the consumption of fossil fuels is heavily taxed compared to other variants. Through this, government would be able to reduce the heavy reliance on such energy. Resource rents has remained a formidable factor of clean environments. To this end, it is essential to deploy modern technologies that are sensitive to climate change in its extractions. Once this has been carried out, its unwarranted negative influence on the climate will be curtailed. Nonetheless, given the validity of the EKC hypothesis in these countries, efforts must be expended to curtail any form of rebound effects. This is only realizable in these countries maintain the ongoing environmental control policies and ensure that the environmental sensitive technologies are deployed in place of the obsolete ones. So this is the end of the presentation. Thank you so much for your attention. You can see my email on the screen, so do not hesitate to contact me. Thank you so much.